Welcome back. I got another Compressonator update for you. I didn't expect to have this one, but there we go. I wanted to look into getting some hard statistical data on the difference between various BC7 qualities. As we know, BC7 at higher quality, like 0.6 for example, takes a long time. And I wanted to say, like, well, how much more quality do we get for that time? And that's taken me on a journey. Included a bomb going off outside or something. I don't know. It was a tire exploding, but whatever. So it's taken me on a journey that I want to explain. But first of all, I'm going to give you the results for those who want to like tune out early from the video. The results are that on the left here, and again, I can't really zoom it in. I guess I could figure it out. Like if you bear with me for a second, I can figure it out. It should be take this, duplicate it, because we don't want to like mess with it too much. Edit, transform. I don't know how to do this. Yes, this is how we do it. And then we can just reset the transform later. Okay, so this is now like a weird aspect ratio, but it's better. You can see it better. Let me make it even bigger. There we go. Cool. I need to reset up my scene collection. So on the left here, what you've got is a bunch of tests, and these are the new ones that I've produced. And so what you can see here, if you read them from left to right, is we're doing BC7 of squares.png at 0.05 quality, and we expect a score, and we'll talk about score in a moment, we expect a score of 89. And so we can see here that we have that exact result, that 005 does 89. So the higher the number, the better. The maximum is 100, and again, we'll go into the score in just a moment. Let's take a look at the second value. So this is 0.1. So we've gone up by 10 times the quality, and it's taken it's about the same speed, and you'll see it's now 90. So we went up by 10 times the quality, went from 005 to 01, and we got one additional scoring point. The difference in time here might not be applicable, because you have to remember, like, it's the first one. Occasionally what you'll see in my tests is you'll see like a run here. This is like the first test. It does a bunch of stuff, and you can see here it takes 4.8 seconds. So if that might be included in the first time here, I need to double check that. Anyway, moving onwards, we can see that now the time starts to actually go up, and it goes up quite dramatically. So now we're at 0.2 quality, and again, we've got 90. So again, we doubled the quality from 0.1 to 0.2, and we didn't gain any additional quality from this metric. And then we went up to 0.3, and we gained a whopping 1.9 minutes. I think we went from 20 seconds to 1.9 minutes. So like that's a minute, like a minute point. I can't do it because it's 1.9 minutes. It's just I wish it would just say it in seconds. We'll just call it 2 minutes though, right? And then that makes it easier, right? Anyway, it went up by a lot. And we can see here that we went from 90 to 94. So 0.2, 90, 0.3, 94. Then I did another one at the quality which we're doing it on Resonite right now, which is 0.6. And you'll see that we went to 95. So for an additional 6 minutes, we got one more simulacra point. I just leaked the name of the thing we're about to talk about, but there we go. That's the summary of that, which is, I think what we can probably look at investigate doing is raising the default minimum quality that I have set from the previous videos from 0.05. We could probably get away with going to 0.2, but we don't really need to, because that, as we said, that doesn't give us any sort of benefit. So we might want to go to 0.3, but then it would take a minute. So I might do another run at 0.25 and we'll see. But we could at least go to 0 0.1 and that would give us 90. Now, why am I obsessed with 90, you're saying? That's because it's the measurement that we're using. The measurement that we're using is derived from an original measurement called SSIM. You can look it up. I don't remember what the abbreviation means, but the original one only dealt with grayscale images because it's quite old. So you can see here that we have the original image here, and what SSIM does is it compares it to a distorted image. You can see as we go here, Albert Einstein's getting blurrier and blurrier, and we can see that this score is going down. So what it means is that a high SSIM means it's as close as possible to the original as possible, and a really low SSIM means it's as far away from the original as possible. So a long time ago, a bunch of people made a thing called simulacra, which was an extension of simulacra of SSIM, and that factored in color channels. And then some additional people, actually just John here, John Sneers, made Simulacra 2, which is the version 2 of this particular algorithm. And here is the source code for that. And you can scroll through here, but this is where our scores are coming from. I just realized that you won't, because I have just done weird stuff here with the thing. Anyway, this is why I don't edit, by the way. It would just drive me mad. Let's just fit to screen. There we go. So here's the image with it getting blurrier and blurrier. So if we go over to Simulacra 2 again, we can now read this, and I can make this bigger, a better way. This originally was a CLI application, which means that what you had to do is you had to take your command line and run these from files. And I didn't want that. That seemed you can do that with .NET, but I wanted to do something a little bit better. Down here, you'll see the scores that we were talking about. So 90 is visually lossless. Distortion is not noticeable by an average observer in a flicker test at 1-to-1 from a normal viewing distance. This corresponds to the typical output of I don't really know what this bit means, but this is something to do with JPEG XL, because this metric is part of that sort of JPEG XL ecosystem. You can see anything above 90 is sort of entering into the mathematical range. What do we mean by mathematical? If we take the image and we compare it to the distorted image, it should match 100%. And you can get a mathematically lossless score with Simulacra if you just put the same image in. So you put the original image in twice, you'll get 100. So you can see that if we now go back to our test scores, 90 here for BC7 at 0.1 quality is fine, absolutely fine. 0.6 was getting us 95, but I don't know if those 5 extra points are worth the difference between 20 seconds and 8 minutes. So that's essentially the whole point of this journey, is to sort of figure out objectively, remove all these opinions, what should we do here? I'm now going to talk to you a bit more about how we got to this point. And that includes how I built what you see here, which is the tests. So I had a long journey. Like I said, Simulacra was a command line application, and I wanted it to be a library that I could call. That wasn't supported by Simulacra, so we now have a fork of Simulacra 2 over at Yellow Dogman Simulacra. And Yellow Dogman Simulacra has, I'm going to I'll pronounce this wrong all day, every day, has an API version of it, which is exposed in a way that means that we can do C# interop with it. So from that, I was then able to create Simulacra2.net, which is a completely open source project. I tweeted about this a couple of days ago, but here it is, and here are those numbers again. You'll see visually lossless, excellent, very high, medium, etc. And they line up to a command line thing. And that's why I wanted to do it, because stuff like this would allow me to call it from C#, have documentation like this where we can say, hey, give me bytes, which means you don't necessarily need to have the file. You could do it in line without writing it to disk, etc. All this sort of stuff works. It also does from file paths though, because that's usually easier. We then take a look at the tests that I've also written for those. We can take a look at the scoring tests here, and we can see what's going on here. So first of all, I test some identical things. This is where we can get some where are we? Scoring tests. Here we are. And they all pass. So this one here, what we were testing here is this is the most important one. We were messing around with apples. So what we have here is a bunch of resources. We have apples. And this is the original image. It's a picture of apples. And then I flipped apples. So this is horizontally flipped. Here is apples quality. This here has a lower pixel quality. I think it's like 8-bit. Yeah, you can see here, bits per pixel 8. All right, then yeah, here we go. Bits per pixel 24, bits per pixel 8. So you can see that the quality has dropped a lot, by a lot. And then there is apple shifted. And shifted is where I've shifted it over to the right just to move the pixels across. So what you can do here is go back to those tests, and we can see, hey, when we pass apples and apples flipped into our test, we expect extremely low because it's really distorted. And when we pass apples shifted, we get extremely low because it's, again, completely different. But when we pass apples quality, we get medium. I'll actually show you that number. I think it's here. I thought it would be down here. Oh, I haven't put it as a console log. I'm looking into test reporting for this stuff, so I can make like really cool plot reports, and you can read them in your browser and stuff, because all of that's possible. So what we're going to do here is do file A, file B. I will have to do the score outside. So the score. Oh, we're doing the... Oh, we have the score here. So we have score greater than or equal to the expected quality. And I just need these to also be that. Oops. And this. And this. And this. I'm almost there, I promise. There we go. That'll do it. So now we can rerun this one. And it's output the information there. Has this transform been weird for like how long? I don't know. To screen? It still looks weird. I don't know if I'm imagining it. Whatever. Send to screen. No, I'm just gonna chalk this one up to tiredness. But anyway, there you go. So now we can see those numbers there. I can also put those. I can put that here. I just gotta change it around a little bit. File B. Didn't expect to do live development here, but whatever. Apple start PNG. And we can reuse these variables here. So file A, file B. Get rid of the expected quality because these are completely different. We would expect a negative score. So again, here this will output our negative score. So completely different. And there we go. Carrots to apples. They're Indeed, very negative, negative 439. By the way, anything lower than 0 basically means like undefined. Like the algorithm doesn't really know what to do. There's no more meaning that you can get from 0. 0 is just like, we have no idea what's going on here. And then these identical ones, you can see that they're much simpler to read here. It's like, hey, we mandate that the score is 100 because we take carrots and we get its bytes. And then we compare the bytes to the bytes, right? These are identical bytes. So there you go. However, we're not done yet. I'll push up those tests as well, because there's just some good new test frequency stuff. We then needed to figure out how to do that in Compressonator. So over in Compressonator, if we go to test expected simulacra score, because now you understand what we're doing, you can see how the test works. So I'll go through it. We do have comments here. We load the original image, so in this case, squares. We set up Compressonator to compress it to the input format, BC7, at this quality. Goes in there. Once we've compressed it, we then decompress it. Now, this is where the fun started, because decompressing an image in Compressonator before this week was very difficult, but I fixed all of that, and now it's quite easy. However, when it comes to a MIP set, we don't really want MIPs. But the block compression really only operates on MIPs. And so what I needed to do to get it back out as an original PNG was to extract that MIP level and convert it into a texture. That didn't exist, so I have added MIP set to texture as a new command to Compressonator. And what that will do is it will take the MIP set here, in this case the BC7 compressed one, take MIP level 0 out of it and store that in MIP 0 texture, which you can see here. We then need to immediately turn around and make a copy of texture of MIP 0 texture that is decompressed. So you can see here that we've got a decompressed copy of it. But this doesn't fill in the data. We need to do that operation. So we use convert texture here, which can decompress. Convert mixed MIP texture cannot decompress, which is the important thing. I think I could edit convert MIP texture to be able to decompress, but I haven't. I don't want to make that change because that would be a huge change. Instead, extracting that texture was the easier way out there. Once it's decompressed, which it must succeed there, we then need to save it so that we can run Simulacra 2 on it. So what we do is we save it to a temporary location, but the problem existed here in the comp save texture. Originally, before today, comp save texture only allowed you to put a MIP set in. It didn't allow you to put a comp texture in, despite the fact that it was called comp save texture. I don't know why, but I jumbled around some code, and now we have comp save texture EX, which can save a comp texture. And then just because we're in C#, we can wrap that with polymorphism such that the user doesn't need to worry that they need to call save texture EX if it's comp texture, or save texture if it's comp MIP set. Like I've abstracted that weird quirk away from it, because that only exists in the native code. You can probably handle polymorphism in the native code. I was just scared, so I did it that way, where it's like an explicit additional function. How did I find this all out? I've been staring at this code long enough that I guess I'm just a Compressonator dev now. This is comp save texture that can only take a MIP set. This is comp save texture EX, which is the extension one that can save a comp texture. Additionally, for very simple formats, we can just go straight through this thing called Stubby. Stubby is a standard. That's not standard. I'll just link it in the video description. It's hard to explain, but basically, like, some guy a long time ago wrote a really cool, really fast, really efficient library to write PNGs, bumps, and JPEGs, and so of course we use it. I just want to show you convert MIP texture. Here's convert MIP texture, and this is the one that cannot decompress, and I'll show you why. If we scroll through here, this line here will take the output MIP set, so in this case, whatever MIP set you want to put as an output, and forcibly, because this is, this is a static line, set it to CF compressed. So what I was doing for hours yesterday was I was passing in a MIP set in that was compressed and a MIP set out that was not compressed, and I was like, that logically means that it should decompress the MIP set, right? Nope. This function, because of specifically this line, cannot decompress. And what actually happens is you fall through some like really intense logic that's like really difficult to explain. I've stepped through, and you end up at convert texture, which remember we're using just by bypassing MIP texture. So what happens here is PMIP set out, channel format gets set to CF compressed. So then we look for channel format. Ignore this because it's not basis. And it allocates channel format here in the allocated MIP set. So what we get when we allocate this MIP set is we get an allocated compressed MIP set. And then we can go down here some more. Still looking for channel format. And you'll see it gets picked up here in out as transcode format, which, trust me, it's compressed as well. And it can't decompress. However, because it uses convert texture, I know it can. I just need to make some edits there to make sure that it doesn't work, have any problems. So that is how we went from, hey, let's get some data on these qualities so we can, evaluate which one we should, ship with. Went from, oh, that'd be cool, to, oh, I've written like 3 NuGet packages and some random functions. Anyway, I hope you enjoyed this impromptu lecture about Compressonator, and do check out the explosion of links in the video description where I talk about the various libraries and commits and stuff that I use to make this work. I'll speak to you soon. If you watch this all the way to the end, send me your favorite variety of cheese.